is Theo. I'm a postdoc at the Haiti Lab, and for this talk, I hope everyone's still awake and have batteries in their laptops, so because we will be doing hands-on coding. Dr. Van Assen has given us a really extensive introduction and talk about all the chest X-ray imaging pipelines, and also what to think about when we want to model our data. This talk is mainly looking at the DICOM images and how you would load them and then work with the DICOM. So by the end of this talk, I hope that you can be more comfortable in actually accessing all the DICOM tags, data elements, loading the images and doing pre-processing. So just a little bit of background quickly. So this is how the X-ray system works. Very oversimplification of it. We have the patient, we have the X-ray generator, and we have an X-ray detector here, and also we have the image processing system. And this imaging processing system in the early days was just the radiologist or the image technician. So now I'll give you some X-ray images, chest X-ray images, and I want to just take a look at this for a second. So we have this first image, second image. They are the same patient, but there's 3 different images for this patient. Okay, just a quick show of hands. Who thinks A is the best image for diagnosis or for the AI model? Who thinks B is the best? Okay. Who thinks C? It's a couple. Okay, that's good. What if I give you the histograms? Does this change your first choice? Who thinks it's A? No one? Who thinks it's B? Oh, sorry. So the histogram is underneath here?
What is a histogram?
Okay, that would be one of the questions. But yeah, so the histogram shows you the distribution of the pixels of the image.
So a histogram is a distribution of the intensities, right? So on the x-axis is the intensity of the pixels, and on the y-axis is how many pixels are of that intensity. So this image here, it's obviously very dark, so no pixels of the brighter intensity. Higher intensity for us is whiter, right? And then middle, and then at the end, relatively even distribution for all intensities.
So you want C? So who picks B as the best? Oh, it's less. Who picks C? Okay, it's actually changed. Interesting. So yeah, so this is a good first step in trying to think about which image is actually the best for AI models for actually being used in diagnosis, and then what do the histograms mean, which Harry already explained. How do we process the chest X-ray images, and what are the common pitfalls in actually processing the images? So we'll touch these questions, and if you have other questions, please feel free to ask. Yeah.
So I wanted to make one point here real quick, which is depending on what you're looking for, one of these images, B versus C, might be better, right? So if you're actually looking for bony pathology, like fractures, C might be better, right? But if you're looking for something in the lungs, C is not going to show you much of anything. Might show you the mediastinum better to look at vessels, right? So this is not a one-size-fits-all solution necessarily. Depending on what you're training your model for, you may want to play with different pre-processing or normalization techniques, right? And that'll apply not just for X-ray, but for any imaging modality.
So let's continue. Okay, so just a little bit of our experience. So last year we looked at our after the datathon, we looked at the data sets that we have, which were extracted as PNGs. And Frank, who is also a postdoc, looked at the distribution of the pixels and found that some of the images had a very high standard deviation of the pixels. So if you were to see the histogram, it might have a distribution like the one in the middle, but there are some pixels that are very, very high on the bright side or even on the low side. So, and we tried to do various techniques such as equalization, normalization, and standard processing methods, but on these PNG images, but it did not produce optimal results. So then what happened was we had to delete these data points, which was not really good because it lowered our total image numbers. And here, for example, is an image where in the previous talk, Mali showed an underexposed image, but you can see the marker, which is this letter L, is a very high intensity pixel. So you can see the standard deviation is very high. So we thought, oh, maybe these standard deviations were because of these markers, which are put on or printed directly on the images. But when we looked through different images that with high standard deviations, we found an image which actually had relatively equal exposure for the marker and as well the actual anatomical regions. And we found that even this one single pixel here, don't know if you can really see it, that one there, contributes to this very high standard deviation error. So what we previously thought that it was the markers turned out to be not always the case. So we had to go back from PNGs back to DICOM. And we looked through the DICOM tags and how do we actually process these images correctly. So we found out that there's this transform, which is called the VOI LUT transformation, which can actually transform this image here to the one on your left, on your right. Sorry. And you can see the difference in the histogram from this histogram and the one on the right here. So the distribution is much better. We still expect low, the highest to be the low pixel values here because of the air, the black pixels, but we have a better distribution of the actual intensity of the anatomical regions. And this is an example of what the VOI LUT looks like when we plot it. So then, so going back to the three images, this is actually the raw pixel data that is actually from the modality itself, and it's in the DICOM file. And the image C is actually transformed using the histogram equalization. So this method of transforming the data is very, very common in computer vision and how we transform our images. And the one that I showed you was called DICOM LUT, value of interest, and it gives us this image which is shown in B. So the standard imaging pipeline, when you input a DICOM image into a DICOM viewer, is actually the DICOM viewer automatically transforms this raw pixel data using its VOI LUT and gives you this image here, which is the presentation state. But again, as Hari mentioned, depending on your deep learning task, then which one should you choose? You can choose histogram equalization or VOI LUT. So we then looked at comparing these two methods. We trained a model, we trained it on data without any of these pre-processing, so the raw images is in group 1. We trained it on only the LUT. We trained it also on histogram equalization, and we trained it on both. And we tested on 2 different external data sets. The first one is CheckSpurt, the CheckSpurt X-ray, Chest X-ray. In this one, so we noticed that the CheckSpurt Chest X-ray data set is PNG, so we can't do anything else. But when we check the histogram, as you can see, is all equalized. So we can assume that they have actually done histogram equalization on their data set. We can't revert it back. We can't do anything else with it. On the second data set was SIM-ACR. So here we have a better distribution here. So we tested it on both of these external data sets and shown that with the LUT, we have better generalization. So it increased performance compared to just using histogram alone. So, and also we have better generalizability because it applies on the data set that was not histogram equalized and also on the histogram equalized data set, and it performed better for both. So here we advocate to use the DICOM file. If you were to share it, create data sets, share with the DICOM file, anonymized version. So now we go back to this image and how is this constructed. We talked about DICOMs, and Judy and Marley has gone through the DICOM. So we looked at, so we changed this into a more digital version. So we have this new imaging processing system, the supercomputer at HitiLab. And so we take the image, digitize it into small pixels. You can think of this as a tabular data set because it's a 2D array. So for those who are used to the tables, this is similar. You can think of it as rows and columns. And each row, each cell here, or we call it a pixel, is based on the attenuation of the photon passing into the detector. So then we take this, we call this pixel data. And then we also have the other metadata, including patient information, acquisition time, equipment information, and so on. We combine this, pass it on as a DICOM file. So this is the basic overall step. There are different file types if you look at different repositories online. So for example here, the SIM-ACR pneumothorax is in a DICOM format. If you click on the mimic chest X-ray, it's a JPEG. Our open data set for embed is in PNGs. We have the NIFTY file, which is mainly for the neuroimaging data sets. And there's the TIFF file, usually for pathology. And here we have a data set for lung-fused CT and pathology. Okay, any questions before we move on to the hands-on section? No? Okay, so if you can get the notebooks from either this GitHub link or from this page. So you can copy the command here, yes. And you go to your terminal. And you can just basically paste it. And it should be pasted in your folder. Okay, so let's go through this. So, oh. You can go to datathon.org/codes.
And so remember these tabs?
So if you're walking through the code and you're stuck, take this and put it like aside and back to the laptop.
we have. There we go. Okay.
Just go back to the Jupyter home and show how you go.
Okay. So when we open this datathon.org/code, you want to go to the bottom, and then it says command to copy home directory. You want to copy this from CP all the way to the end. Hit copy, and then you can go to your home folder, click on this plus icon, go down, click on the terminal, and you can paste it, and then press enter. And it should copy this file, folder. So inside the folder, there are two additional folders. The first one is CXR, data preprocessing, and the second one is embed. So the embed is, we'll be using this on Wednesday. So if you go into the CXR data preprocessing and open the CXR data preprocessing notebook, which is this one. I have it open here.
So have people at least opened the CXR preprocessing module? Okay.
Okay. So the next step is to change your kernel. So by going up here, mine says pandas. Yours might say IPY kernel. So you want to click on that. Change it to pandas by clicking on it, pandas, and then select. Okay, so, and now it should say pandas. You can run your cell by clicking on this play button, or on Windows it's Control Enter. I don't know what it is on Mac. Command, Shift Return. Okay. Oh, sorry, it's Shift Enter. Sorry, yeah, Shift Enter. So the first section here is just we want to load our libraries. What we are using here is pandas, NumPy. So this is another. It's a numerical Python package library where we can do more computations. Matplotlib is a visualization library so that we can actually show the images in the Python environment. Pil here is a Python imaging library, and we want to use this when we want to save it as a PNG, so when we export the data. The rest, so Glob OS is mainly for working with the files. CV2 is OpenCV, so Open Computer Vision. It's another Python package for computer vision processing. So the first section, we'll look at basics working of working with DICOM files. We'll be working with one chest X-ray image here. So here we will do another import. We'll be using PyDICOM. So PyDICOM is our main DICOM library that we use in our lab. And you can click on this link here if you want to read more about PyDICOM. There are other libraries like ITK Snap, but we use PyDICOM. The next cell here loads the file. So this is the path to our DICOM file. As you can see, it is the extension is .dcm. You can have .dcm, .dicom, doesn't matter. So the file name here is actually the SOP instance UID. So if you remember, Judy showed the different levels: patient ID, study ID, series, and then the instance. So this is the instance at the instance level. And we can load the DICOM using PyDICOM DCM read. Just click on enter and go to the next cell. You can actually see all the DICOM tags that are within this DICOM file. So we have the metadata. It consists of mainly 3 elements, 3 columns. The first one is this numbering system, number tag, 002, 000, and then this is the description of this DICOM tag. So this is the DICOM tag, this is the DICOM tag name, and this is the value, so 108. If you want to see here, there's the transfer syntax UID, JPEG lossless, and so on.
Anybody have questions? Yes?
The DICOM values here? They are the values of this DICOM tag, DICOM data element. So for example, if you want to see the accession number, so this is the accession number. It's the study number of this patient.
So DICOM files are a container, okay? And that container contains not just the image, but all of the metadata associated with the image that comes from the scanner, right? Patient ID, study date, manufacturer, technical parameters, grid size, how much radiation dose. That's that 700 to 1,000 tags that we talked about. So you'll hear it referred in different ways. We'll call it headers, we'll call it metadata, we'll call it key value pairs. There's a bunch of public tags that are defined, which is what Theo's showing here. There's also private tags put in by specific manufacturers. So on the left, that 0080033, for example, for content time, that first set of numbers in parentheses is the value of that tag. So in every DICOM file, if there is a content time tag, it'll be 0080033. Content time just makes it readable for us, but the index or the key of that tag is what's on the left there. The value is what's on the right, so it's blank, right? But this. I want to make sure everybody understands that this is important to understand DICOM files and their contents and how they're set up. And then the image in the DICOM file is in a tag or a header or metadata element called the pixel array. So there'll be one called pixel array, typically not shown here, but you can pull it up and you'll get an array that is the dimensions of the image. So if it's a 2000 by 2000 pixel image, you'll have a 2000 by 2000 dimension array, and every entry in that array is the value, the intensity value of that pixel. So DICOM files are entirely self-contained for the image that they represent and all the metadata of that image. Does that make sense?
And just to add to that is that DICOM is the standard. So if you see this DICOM tag 0080070, and the name is manufacturer, this is going to be across all the DICOM files. It's going to be this tag. So whether it's chest X-ray, CT scans, any modality, this DICOM tag is the standard. So if you want to open a DICOM tag and then find the manufacturer, so you go to this tag. So the next aim is to get comfortable in accessing these values. So one way of accessing it is you can use the actual value of the tag. So if you were to pull up the patient ID, for example, what you can do is take this value here and copy it here, but add a 0x in front of it, which is the hex decimal. An easier way is to use keywords in Python. So we can do dot keyword, and then it will give us the patient ID. And if we just use this patient ID, we'll get this DICOM tag called patient ID, and the patient ID is the following value. We can look at the tag, and it gives us the DICOM tag. We can use it. You can use the name, and it will give us patient ID, but with space. right here. And if we want to know the value, we can do dot value. And a much simpler way to get the value is directly calling the loaded DICOM and using this dot method and calling the attribute patient ID, and it will give you the value. So in the next cells, I don't know if we have time to do exercises, but we can just move. Okay, yeah, you can do the exercise. Yep.
There's exercise 1 and 2. Just do it at home.
Yeah.
Just follow the same. Just read the complex, the marking of the head. Will provide the answer.
Yeah. Okay, the next session is now we're going into the images. So the image, as I shown in the PowerPoint, is called pixel data. It's in this 7FE00010, but you can't call it pixel data. The thing is with pixel data is that it is actually encoded bytes. So we cannot work with this directly. Because there's this encoding, we talked about this, there was a question about the compression, and in the header there's this compression or encoding using JPEG or other types of encoding, and so this data here is actually encoded and we need to decode it. But with PyDICOM, as Hari mentioned, we can directly call pixel array, and it gives us an array of these pixels. So this is a two-dimensional pixel. Now we can save it as a variable image. We can see the shape, which is 1622 by 2021 pixels. We can see the minimum value and the maximum value here. The minimum value is 2000 and the maximum value is 16,000. We can load and see the image. This image, as you can see, is underexposed image as shown previously with very high intensity for the label, and we'll be processing this. If you go through, so the first one is using modality specific units. So there's two steps. The first one is applying the modality transformation. So what is the modality transformation? We would transform the image based on what the modality is. So for example, in CT scans, we want the values to be in Hounsfield units. That is what the standard unit of the pixel values, or in CT is voxels, of the actual images. So in radiography, or in this example, it's just pixel values. And it is determined based on, so the range is determined based on the bit. So the bit of the image. Here's another exercise to ask you to load the bit size of the image. So to do this, we can call, yep.
Questions? I just want to give everyone a second to ask. That makes sense?
The clue for that exercise is that the bit size will be in the metadata.
Yes, it will be.
Someone just has to go back to the metadata.
So yeah, you can take a look at the metadata tags and see if there's anything that might represent the bit depth of the image. Alternatively, you can look at the range, the min and max range of the pixel array. If the maximum pixel intensity is 60,000, right, then you can't be a 12-bit image, right, because 12-bit doesn't go that high.
Yes. Imaging modality, so you have CT scans, you have MRIs, you have ultrasound. So those are different modalities. Yeah.
Different types of cameras, like Nokia phone, Android, iPhones.
Yeah. So this is the equation to do modality LUT transformation. So the first one is a linear transform. So y equals mx plus b or plus c. These values here are based on the rescale slope or rescale intercept in the DICOM tag. You can calculate it by yourself, taking these and applying the transformation. So in chest X-ray, it's just 0 and 1 because there's no transformation. But for other datasets, for other modalities, you have to normalize it. There will be a transformation happening. But PyDICOM also allows us to quickly do this because it provides a function called apply modality LUT, so you can directly use this function. Oh, here I actually wrote the functions to do it, but yeah, this is showing that by applying the rescale intercept and also rescale slope, we achieve the same pixel values across all the pixel values. Here we're loading a CT scan example and applying the modality LUT directly on the CT scan. So you can see the image doesn't look any different, but when you look at the values, so the original minimum value was minus 2,000. The original maximum was 2,200, 2,800. When we did the modality transform, it's minus 3,000, and the maximum is 1,800. And we can say these are in Hounsfield units because they have been transformed. But image-wise, you can't really see a difference. And then the second step is actually applying the VOI LUT. And there are two equations to do this. The first one is a linear equation using window center and, sorry, this one, based on the window center and window width from the DICOM tag. But if the DICOM tag specifies it's a sigmoid, which is a nonlinear transform, then this is the equation. And again, PyDICOM already provides us with the functions, so we can easily use that. This is the sigmoid function or the nonlinear transform that is available in the DICOM tag, sorry, in the DICOM file. Then we can combine the two functions, so apply modality LUT and then apply VOI LUT here as one function to quickly apply it to all.
Okay, checkpoint. What are we doing when we apply a modality LUT or a VOI LUT to an image? What are we accomplishing? Gotta be, not you, Judy. Come on, speak up. Transformation, okay, of pixel intensities, okay, right? Why are we applying a transformation of pixel intensities? Make contrast. Okay, redistribute the pixels on the images. Okay, good. So avoid outliers, right? Super intense or super washed out images. So all of this stuff that we just did, I just want to make sure that we zoom out and talk about the big picture, right? What is the function here? The function is, so the challenge is the bit depth of DICOM, whether it's 12-bit or 16-bit, is more shades of grayscale than human eyes can perceive and more shades of grayscale than a monitor can display, right? So when we look at the raw data of the image, and if the range is from 0 to 65,000, we cannot perceive that. And maybe if you had a super deep model, it could distinguish between those. But what do we want to do? We want to bring all of those intensities into a range that is sort of human readable or more clinically relevant or anatomic relevant, right? So go down now, Theo. So you have your raw image, you have your VOI LUT transformed image, and then modality plus VOI LUT. On the left two images, you can't see the brain tissue, right? It's not that the data is not there, it's that the intensity distribution of the images, of the pixel data, is in a form that we can't see those differences. Our eyes and this projector cannot display the difference in intensity between those images. So it brings them into a range that is perceivable to train the model. That's what we're accomplishing here. You have to do this for every medical image. You don't have to do it for natural images because they're captured and processed with, well, it's done by the camera, right? natural light is processed, but that's what we're accomplishing here. I just want to make sure that that concept is not lost. Questions? Yes. So what? Yeah, that's what. So Theo kind of there's a cell in there. So for a CT scan, you would process every slice in the CT scan. So in a CT scan, if there's 25 slices or 100 slices for the head, you're doing this transformation on every single slice. The DICOM, the transformation function is there, and it may be the same transformation function for every slice, but it needs to be applied.
Thank you, Harry. So, yeah, so here we are showing that it's actually being applied, modality LUT and also the VOI LUT to each slice. These are the samples of some of the slices. You can actually go through and modify this plot to visualize more slices if you want. And then now we apply it on the chest X-ray image. And so we have, from the original image, applying that transformation, we get this final processed image. And so this is the answer to the previous. So there's bits allocated and bits stored to look at the bits of the image. So now we can experiment with histogram equalization. This is where we use the OpenCV library called equalize histogram function. Image on the left is the histogram equalized image, and on the right is the VOI LUT image. As you can see, differences there. We can also plot the histogram. So it's roughly equal across all the different intensities. Yep. Yes, so the warning sign here is because it's in the PyDICOM library handler. What happens is if the apply LUT function receives a float data type, it throws out this warning. Because we are, if we go back to the process, so we're applying the modality LUT function first, and this output is then passed into this function here. The output of this is a float data type, and when it's applied here, it gives this warning, but it's not an error, but it's just a warning. Okay. Any other questions? Yes?
Back to the hyperlink where we can copy all of this stuff for the terminal code.
Yes? Okay. Next, we'll be saving the PNGs. So if you run this, then what you will have is you should have a folder called outputs. So in this output folder, you would have a single PNG file, and which is the output of the processed chest X-ray. So what we've done in our chest X-ray data set that you will be using is that we've actually done all these processing steps, and we've saved them into PNGs for you to use for training. So this is what one of it looks like. And finally, the final section is common normalization techniques. We've like gone through this. Like Saptashi's talked about robust scaling, min-max scaling, and on the tabular data set, this is basically the same concept but on images. So here we have min-max normalization, And also the second one, which was called robust scaling in the tabular data, is called standardization. So the first one is min-max normalization, where we want to bring the distribution of the pixels between a minimum and a maximum value. It's usually between 0 and 1. So what we can do is taking the actual image minus the minimum image divided by the range, and that will give us an image with a value between 0 and 1. So we can check that by looking at this function, method here. So the minimum value now has been transformed to 0, and the maximum value has been transformed to 1. We can plot the image and compare with the processed image. There's not a lot of difference in terms of visualization, but when you see the values, so it's supposed to be the original, the processed image. The minimum was 50, the maximum is 16,000. Now the values have been transformed, squished, the distribution has been transformed to a distribution between 0 and 1, as you can see. And the last section is standardization, or in tabular form was robust scaling. So the aim of this is to push the data set into a normal bell curve or normal curve. So we want to push the mean of the distribution to 0 and set the standard deviation to 1. So what we can do is using this equation, so we take away the mean and divide it by the standard deviation, and it will result in a mean of 0, or here it's very close to 0 because of floating point errors in computing, and the standard deviation of 1. When we look at the image, again, similar, there's no big difference in the visualization, but when we look at the actual values, we have the mean, which was previously 9,000, and the standard deviation of 3,900 pixel values. Now the mean is 0, and the standard deviation is 1. So we do this mainly for before putting this image into the model, the AI model pipeline, is to better help the gradient learning for the model. It helps in training, and also normalizes the data so that like when we receive a model from external data sites, or when we want to apply it to other data sets, this standard, the preprocessing is standard across the sites and also across data sets. Yes, Chase. From experience, I tend to use the standardization. So the problem with min-max, although it's also common, is that it is sensitive to outliers because you have the maximum value or the minimum value that can skew your distribution. But with standardization, it is robust to outliers, but it depends on the model that you're using. Oh, it's not? Okay. Please correct me. That's what I've been taught.
So min-max scaling, standardization is less sensitive to outliers, but not completely insensitive to outliers.
Okay.
So with min-max scaling, understand that whatever your smallest value and whatever your largest value is, that's dictating 100% of your support, the support of the distribution. With normalization or standard normalization, your support of the distribution is dictated by the standard deviation, which means it still can be influenced by large values, but it's not directly defined by a very, very large value. It is influenced by the large value, but it's not directly defined by it. If you want to get around it, you could use something like a trimmed mean, but regardless, this is where we would say, please don't use any technique without checking the results first. You're not a computer. You use computers, but you're a human being and you have intuition. Please use it.
Thank you. Yeah, that's fine.
I have two comments to add here. I think you were doing PPI in the PhD show, and that's different from what's in the image because the pixel spacing in the image might be different. So in the DICOM tag might be different. if this was lossless JPEG, right, and you're doing the PNG conversion, so PNG is the lossless format, so it would not be the same because the pixel in the lossless JPEG would be different from the pixel in the PNG format. So you have to actually take that into consideration. There's a small nuance there. So if the modality captured it in lossless JPEG, you have to be careful to actually use lossless JPEG rather than if you go to the code, you see, yeah, that thing, right? So that DPI is artificial, like set manually, but there is a DICOM tag called pixel spacing that shows the actual modality is pixel spacing. And that, so what you see there may not be how it's actually meant to be seen by the modality.
Yeah, so the DPI in Matplotlib changes how big the actual image is. So if you change it to 90, for example, it will make the image smaller. If you make it 600, that's the maximum for the screen. It still be same, yeah, but see.
Two more questions. There's one there.
So I have one question. While doing the normalization, is it advisable to remove the black portion which is visible in the images, because those pixels are very high, so they might impact the normalization of the images? What